Welcome to the viewers. Now we discuss the nature of recurrence relation in Hermite polynomial. We proved in earlier days the part 1 formula, and we prove here the next recurrence relation of Hermite polynomial. Twice z hn z is equal to twice n hn minus 1z plus hn plus 1z. We have to prove this relation. Now for the part of proof. Now we have considered sum of n equals to 0 to up to infinity hn z by n factorial t to the power n. We know the generating function, and already we considered in my earlier reference of my earlier videos. If the students who are not watching and who are not able to follow my earlier videos, t to the power twice tz minus t square. But here if we considering these terms, t is eliminated here, but there are the two relationships hn minus 1 and hn plus 1. So it is clear, in earlier recurrence relation we taking the differentiation with respect to z. Here we take the differentiating both sides with respect to t. So differentiating both sides, taking it equation number 1 of 1 with respect to t, we obtain sum of n equals to 0 to up to infinity hn z by n factorial with respect to t, that is n t to the power n minus 1, and here we consider that is from the exponent power twice z minus twice t into e to the power twice tz minus t square, which imply sum of n equals to 0 to up to infinity hn z by n minus 1 factorial into t to the power n minus 1. And here we considering the sum of 1 from 1 to up to infinity, because if we split this term m equals to 0 to up to infinity, n equals to 0 to 1, that term will be abolished. That means if we considering that for the term n equals to 0, we consider that term doesn't exist. So this term came from n equals to 1, and also we follow, if we follow this result, n equals to 0 not defined because minus 1 whole factorial is undefined. So it will be 1 to infinity. Here it will be twice z e to the power twice tz minus t square minus twice t to the power twice tz minus t square, and sum of n equals to 1 to up to infinity hn z by n minus 1 factorial t to the power n minus 1 twice z. If we substituting this value, that will be this result. So it will be sum of n equals to 0 to up to infinity hn z by n factorial into t to the power n minus twice t, sum of n equals to 0 to up to infinity hn z by n factorial into t to the power n. And it's clear, sum of n equals to 1 to up to infinity hn z by n minus 1 factorial t to the power n minus 1, that is sum of twice z, sum of 0 to up to infinity hn z by n factorial into t to the power n minus 2, sum of n equals to 0 to up to infinity hn z by n factorial into t to the power n plus 1. And we follow up to this step. Now if we consider here this type of result, we find here only, that is replacing n by n plus 1 in the LHS term. So it will be n equals to 0 to up to infinity hn plus 1z by n factorial t to the power n, because we are taking as a whole shape of t to the power n form and equating the coefficient. That's why n is replaced by n plus 1. So n plus 1 here, it is n plus 1 minus 1, that is n factorial. N plus 1 minus 1, that is t to the power n, twice z sum of n equals to 0 to up to infinity hn z by n factorial t to the power n. And here it will also change because it is n plus 1. We are considering only t to the power coefficient of t to the power n term. So n will be replaced by n minus 1, and here the terms change, comes from 1 to up to infinity hn minus 1z by n minus 1 factorial into t to the power n. Here also changes, n comes from 1 to up to infinity because 0 is not defined. Now we considering the coefficient of t to the power n. For we considering here equating the coefficient of t to the power n, we obtain hn plus 1z by n factorial is equal to twice z hn z by n factorial minus 2 hn minus 1z by n minus 1 factorial. Therefore, if we multiplying all the terms by n factorial, it will be hn plus 1 z twice z into hn z minus 2 into n factorial by n minus 1 factorial, that is n into n minus 1 factorial by n minus 1 factorial hn minus 1 z. And if we derive this result, that is multiplying on both sides by n factorial, that is n factorial will be written as n into n minus 1 factorial, and it is also written as into multiply into hn minus 1 z. So it will be cancelled. Finally it will be hn plus 1 z twice z hn z minus twice n hn minus 1 z. It will be our result. Therefore we can see twice z hn z, that can be written as twice n hn minus 1 z plus hn plus 1 z. Now we proved our desired result. That is a part of proof. Another interesting result, and we prove this result. And just once more, if we derive another result from here, if we take for n equals to 0, we get particular result. This term will abolished and we considering only the second term, that is next result for our derivation. For n equals to 0 in 2z hn z is equal to twice n hn minus 1 z plus hn plus 1 z. We have twice z h0 z, and this term will abolish for n equals to 0. So here we find h1 z. This is also our derived result. It is also sometimes some question will be given to prove this relationship. It is a derivable result. May come in the examination. We end our discussion today. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks for watching.